Here we're going to introduce a new quantity, namely momentum, and compare and contrast it with one we've already talked about, namely kinetic energy. We'll start by looking at the following situation. Here we've got poor Al in between two boulders that are rolling towards him. In one sense, there is no net motion involved. We have a certain amount of motion going to the right and an equal amount of motion going to the left. So in one sense, there is no net motion. But Al certainly has reason to be worried because there is going to be something that's going to happen. Namely, something's going to change from this motion that could harm him. And here we'll have to look at what exactly is going on here and why do we have basically two different kinds of ways to describe what's going on here. In one sense, we can describe the amount of motion here using vector quantities, and we can also describe the amount of motion going on here using scalar quantities. So let's start by just physically defining what we mean by momentum. Momentum is simply defined, as Newton did, as the quantity of motion, or the amount of mass that is moving times its velocity, or P equals mass times velocity. This is a vector quantity because we're taking a scalar mass, multiplying it by a vector velocity, and that gives a vector result. So momentum is a vector, and notice it is in the same direction as the velocity, because we're simply changing its size by multiplying by the mass. Now, sometimes when we introduce a new quantity, we introduce new units, like we did with energy. Here, we are not. This is just for historical reasons. There's no special name for the units of momentum. So they are just units of mass times units of velocity. Now, we can also look at Newton's second law of motion, F equals ma, and rewrite it a little bit and saying it's mass times the change in velocity divided by a time interval. Then take the mass and multiply it by the change in velocity. And this right here is just the change in momentum. So in one sense, force is just the change in momentum divided by the change in time. Or we take the limit as these changes become infinitesimally small, we see that the force is the rate of change of momentum. This is just an alternative way of writing Newton's second law. Now, just like we did with work, we defined work as the multiplying force times the distance an object moved. Here we're going to take something a little bit different. Instead, we're going to ask what happens and what is the cumulative effect of applying a force during a certain period of time. I'm going to add up all of those small infinitesimal changes, and we're going to end up getting the overall change in momentum of an object. And we're going to call this force times time. We're going to call that impulse and use the symbol J. Now we're using the symbol J because later on we'll use the symbol I for moment of inertia. So here we will use J. So another way of writing Newton's second law by integrating this is to say that impulse equals change in momentum. Impulse, just like work, is the area under a curve, only here it's the graph of a force versus time. So here if I've graphed the force between two objects and the time during which it acts, we notice the impulse is simply the area right here. Now, why do we have both kinetic energy and momentum? Kinetic energy depends on mass and velocity, and momentum depends on mass and velocity. They're different combinations of mass and velocity, but they seem to be strongly related. In addition, we can take kinetic energy, multiply and divide by mass, and we find kinetic energy actually equals p squared divided by 2m. Our kinetic energy essentially is just directly related to momentum. So why do we need both quantities? And this is because when two objects interact, they do in fact change each other's state of motion. But something about the overall motion remains the same, while something else about the overall motion changes. What stays the same will be the amount of momentum. That will rigorously stay exactly the same. What will change or allow changes to happen will be energy, because energy will change form from kinetic to potential, for an example. So let's consider an example. Here we've got a football player, Mike, who's carrying the football down the field. He could be tackled by two different players in the other team. One is Speedy Gonzalez, and the other is Ponderous Poncho. Using the numbers here, Mike's weight and Mike's speed, and the same for the other two players, which one will be more effective in stopping Mike? I want you to think about that for a moment and enter your answer into the Google form that is attached to this video. Well, it turns out they will both have the same ability to stop Mike. And that's because, notice in both cases, there is no overall net momentum. The momentum here, if we use English system, is 200 times 8, or 1600. Speedy has the exact same, 16 times 100, exact same amount of momentum. Ponderous Poncho is 4 times 400, the exact same amount. There's no momentum in the first case, and there's no momentum in the second case, so when they collide, there will be no net motion. This is exactly the same situation as we saw with Al at the beginning. Momentum is the thing that stays the same. There was no net momentum before they collide. There will be no net momentum after they collide. However, from Mike's perspective, he might worry about which one of those two potential tacklers will be more likely to harm him. Will it be Speedy Gonzalez, Ponderous Poncho, or will it again be the same? Again, answer the question on the Google form attached to this video. And we see the answer here is different. Now it's Speedy Gonzalez, and that's because he has more kinetic energy than Ponderous Poncho does. Kinetic energy is what you need, or energy in general is what you need to break bonds. And that's exactly what poor Mike is worried about, namely bonds in his body being broken by the energy going into this collision. And Speedy brings more energy into the collision than Ponderous Poncho does. And therefore, it's more likely for that energy to break bonds in Mike if it's Speedy versus Poncho. Energy is what allows changes to happen, because energy can change form. Namely, we can rearrange the atoms in poor Mike more readily if I have more energy. These situations show that energy is indeed quite different from momentum. We're going to look at energy as the ability to cause internal changes, or changes in structure, or the ability, if you will, to damage something. Momentum, on the other hand, causes only external changes in the overall motion of an object. For an example, the motion of its center of mass, or it's the ability to bring something to rest. Kinetic energy and momentum are different aspects of motion. Because energy can change form, energy is what can basically cause changes to happen. Momentum does not change form. Momentum, when we say, has both magnitude and direction, that is what does not change. Let's consider another case. Here we've got Jenny, who's at rest, and is going to start running. As she runs, she's going to gain a certain amount of momentum. She'll be a certain amount of inertia that will be moving, so she'll have momentum, but she'll also have kinetic energy. And I want to compare how much momentum and energy she gains versus how much gets transferred to the ground or the earth. Notice we have two different questions. So first I want you to consider how much momentum Jenny gains versus how much momentum the earth gains. And again, put your answer on the Google form. Well, here it turns out they're exactly the same amount. Whatever momentum Jenny gains, the same amount of momentum must be transferred to the earth, just in the opposite direction. However, we'll look at kinetic energy. She gets considerably more kinetic energy than the ground does, or the ground gets considerably less than she does. We can understand that by considering the differences between impulse and work. Impulse is force times time. The forces, whenever two objects, for an example, Jenny and the earth, interact, the forces are always equal and opposite due to Newton's third law. In addition, for whatever amount of time Jenny pushes on the earth will push on her for the exact same amount of time. As a result, the impulses must be the same, and the exchange in momentum has to be exactly the same. Work, on the other hand, is force times displacement. While the forces have to be the same, the distances that each move will not be the same. So consider the displacement using kinematics as 1/2 at squared, nominally plus the initial velocity, but we said they started at rest. The acceleration will just be the force divided by the mass. So in the case of Jenny, that will be the force between her and the ground divided by her mass. In the case of the Earth, that'll be the same force, but now divided by the much larger mass of the Earth. As a result, the distance the Earth moves will be very small. The distance Jenny moves will be very large. As a result, the work done on Jenny will not equal the work done on the Earth. Jenny will have more work done on her. She will gain more kinetic energy. The Earth will have considerably less work done on it. It will gain considerably less energy. However, that doesn't mean we violated any conservation laws, because remember, the energy comes from changing forms. The energy came from the food Jenny ate. That gets burned and turned into both her kinetic energy and the Earth's kinetic energy. And work is the conversion of energy from one form to another. So work is being done on Jenny to basically transfer energy from one form, chemical, into another form, kinetic. The same thing for the Earth. Momentum never changes form, nor does it change direction. Notice we haven't talked too much about two dimensions, but when we say momentum is conserved, we mean momentum in the x direction will be conserved separately from momentum in the y direction. We can't convert one direction to another direction. In addition, momentum is never converted into heat or thermal energy. It stays as momentum. Impulses merely transfer momentum from one object to another. Let's consider what happens when an object is set into motion, moves for a while, and then stops. Where does the motion come from? Well, essentially it comes from some form of potential energy being converted into kinetic energy, into motion. However, as this is done, there can be no change in momentum, so whatever is moving backwards must have an equal amount of backward motion, so there's no overall change in momentum. Whenever something is set into motion, something's moving forward, something else is always moving backwards. When it comes to rest, what happens to the kinetic energy? Well, the kinetic energy can be converted into heat via friction, which is a non-conservative force. The momentum, on the other hand, is just transferred to the Earth, and usually don't observe that because the change in motion of the Earth is infinitesimal. But for here, the momentum merely gets transferred essentially back to the Earth. We had the Earth recoil as you're set into motion. When you stop moving, you apply a force in the opposite direction to rechange the momentum of the Earth back to what it was. Now, in summary, we have momentum and energy. Momentum is a vector quantity, while energy is a scalar quantity. Momentum will turn out to be strictly conserved. It's never converted into anything else. It's never converted into heat. And later we'll see it's also not converted into another type of momentum, namely angular momentum. Linear momentum is a separately and rigorously conserved quantity. Energy, on the other hand, while it's always conserved as a whole, it can change form from kinetic to potential. Momentum is the thing that always stays constant. Energy is the thing that allows for changes to occur. And that's the key difference between them. Now, the last thing we might want to consider is, okay, why did we introduce the concepts of energy and momentum? In one sense, Newton's laws of motion, F equals ma, and the force laws we've introduced are all we really need to do classical physics. We can predict the motions of asteroids. We can send rocket ships to other planets. We can, in fact, solve all the problems in classical physics with only Newton's laws and force laws. Conservation laws are introduced in part, which is not mentioned in most classical textbooks, because it's one thing that brings us to modern physics. In modern physics, we don't talk about forces and accelerations. Instead, we say interactions will end up being the exchange of particles, and the particles will carry energy and momentum. We will not talk about forces. And the changes will be changes in quantum states that will be governed by the uncertainty principle. So the reason we introduce energy and momentum, in many respects, they bridge the gap between classical physics of Isaac Newton and the more modern physics of Einstein and Bohr.